Okay, so now we're going to talk a little bit about the basic notions of probabilities today. This is a part of the lecture that we're going to have uh, the next week. We're going to be discussing these topics, and this is going to be on the test number 2. So this is not going to happen on the test number 1. It's going to be on the test number 2. Okay. Uh, I think most of you have some idea what a probability should be, so this is not going to be much of a surprise, but we also need to have formal ideas about formal notions so that we can be quite clear what the idea of probability is. So first of all, we're starting with a notion of experiment. Experiment is something that is going to happen, uh, and it's going to end up with a random outcome. Anything like that we can consider an experiment. The experiment could be something that is very simple, or could be something more complicated, but it has to have at the end an outcome that we have an idea that might happen, but we have no control over whether it would happen or it would happen something else. So, for example, I have a couple of examples here. Roll of a fair die would be an experiment, and the idea would be that at the end you would have something on the top of the die. There'd be 1, 2, 3, 4, or 5, or 6, and that would be considered to be a successful outcome of that experiment. Of course, I don't know what else could happen. For example, die could disappear after you roll it, rolls over somewhere, and you can't find it. That would be unsuccessful experiment. So we only consider a notion of an outcome when the experiment ends up with something that we consider to be a successful experiment. So the outcome of this particular case would be the something coded. So we're going to code that as 1, 2, 3, 4, 5, or 6, just like here, right? So that would be the idea what an outcome is. Again, this is not a full description of things. So for example, I could say, oh, I rolled a die on the table, the die fall off the table, roll underneath a piece of furniture, and I found it there, and it says on the top of the die I can see 1 indentation, there will be 1. I don't need all of that. We just need the coded outcome 1. So no matter how the die was rolling, when the top of the die shows up 1 indentation with some color in it, that is 1 for me. Okay, I'm guessing you know what a die is, right? Gambling die. You could also have tossing a fair coin twice, and again, there could be things that could happen that are different that we expect to be an outcome, but we do expect outcomes to be heads, heads, heads on the first toss, heads on the second toss, heads, tails, heads on the first toss, tails on the second toss, tails, heads, tails on the first toss, heads on the second toss, and tails, tails, which would be coded as HH, HT, TT, EH, TT, which would be a code for the outcomes of this experiment, that is tossing a fair coin twice. Another experiment could be taking a blood from a random person and determining blood type. Now we have 8 different blood types: A plus, A minus, B plus, minus, AB plus or minus, and O plus or minus. So those are the outcomes. Again, you could have something else happening, like we have a contaminated sample and we couldn't find the blood type, so nothing happened. But we would consider that to be unsuccessful experiments, so they would not be in the notion of an outcome. So outcomes are just coded, right? I'm not interested in all of the details, how the blood type was processed, how the blood sample was processed until we determined blood type. I'm not interested in that. We're just interested in the end of the story, which is the code of the blood type that was determined. Okay. Another experiment would be if I throw and we'll leave some trace, and that would be a point on the board, point somewhere on the board. I would code that by the coordinates of the point. So I could say, now this point I just hit would be 0.5 for an X, and it would have about 0.4 for a Y. So now I have a point. 0.5 x, 0.4 y. That's a point on the board. That's an outcome. Now this time I have way too many outcomes. I could have any point on the board here to be an outcome of my experiment. And I could also hit something outside of the board, or I could hit the board not with a tip of a pen but the other end or something else. Those would be unsuccessful experiments, so I'm just going to consider when I hit the point on the board with a tip of a pen. That would leave a mark on a particular point on the board. So that would be another example of an experiment with random outcomes, but that experiment would be with infinitely many outcomes, because there are infinitely many points on this board. Okay, so now the next notion of probability that is important to us is the notion of a sample space. Now, probabilistic sample space is just basically the set of all of the outcomes. So the only thing you're gonna note here is that instead of just listing them in a row, I am now including them in the set. And the notion in mathematics, notion of set is something like this. You put the wiggle brackets and then you put a list of the things that you have in the set. So I would have here what I just listed, 1, and then whatever else you want to write here, and all separated with comma. So it might be, I don't know, 1, 8, comma 9, 10. That's what we call a set. This set has 4 numbers and not particular choice, and we call this a set. So whenever you have something like that, it's a set. So sample space, probabilistic sample space, is a set. So it's going to have a wiggle brackets. It's going to have something in it. What is that something? Well, it will be all of the outcomes of a particular experiment. So sample space is associated with experiment, and vice versa. Experiment has a sample space. In the sample space, you have all of the possible outcomes of that experiment. All of that, the outcomes you consider to be an outcome of a successful experiment. So here is a sample space of the rolling a fair die. Here's a sample space of tossing a fair coin twice. Here's a sample space of determining one's blood type. And if you look at what would be a sample space of tossing a marker into this board, well, a sample space would be set of all of the points whose x is somewhere between 0 and 1 and whose y is somewhere between 0 and 1. Any point like that will be in your sample space. The sample space is an infinitely many outcomes, because I just said that I would label those points with the coordinates, something for an x, something for a y. And since I know I have on this board infinitely many points, I have infinitely many outcomes. But you can just simply write 1 by 1 board. It's not exactly 1 by 1, it's more like a little longer than 1 meter by maybe, I don't know, 1.6 times 1.2 or something like that. It doesn't matter. Really, I have actually a set of all of the points whose coordinates are between 0 and 1, x coordinates and y coordinate. And there are infinitely many other points. So this time I wouldn't use a wiggle bracket, I will use a different symbol. In mathematics I will use I time I, which is the symbol we use for 1 by 1 board in mathematics, but that would be a sample space. A set, again, set of all of the points that are on this board. Okay, now when we talk about probability, we always talk about the probability of an event. Something that happened, the probability of an event. So you need to have an event. Now what is an event? Event is any subset of a sample space. So for example, if you look at this first example of a sample space, 1, 2, 3, 4, 5, 6, which is the sample space of rolling a fair die once. then the event could be 5, 6. 5, 6 is an event that you can call it no less than 5. No less than 5, if we are rolling a fair die, means you either have 5 or you have a 6. It could be something else like 1, 3, and 5. I guess I would call that odd. I'm betting that the roll is gonna be odd. 1, 3, or 5. And again, this will be an event. How many events you can have here? Well, in this particular case, you could actually have 64 different events. Okay? You can make 64 different sets, subsets of this set 1, 2, 3, 4, 5, and 6. Right? This looks somewhat surprising that you can have that many. I just wrote 2. One is here, 5, 6. Another one I wrote 1, 3, 5. You can write 64 of them. That's how many. In case of flipping a fair coin twice, this would be an event HHHTTH, which you can call it at least one head. At least one head. So this is 2 heads on the first and the second flip. This is HT is heads on the first flip. TH is heads on the second flip. But in any case, you are talking about here about 3 out of those 4 here that you have in a sample space. Sample space itself is an event because it's its own subset, right? The idea about subset is you take anything you have in the larger set and put it together and call it a set, put the wiggle brackets, list them, call it a set, and that is a subset. So subset could be everything also. You can take everything and reassemble the set and you have a subset. So we also consider the subset to be the empty set, which is, this is a notation, Greek phi is the symbol for the empty set, which is the same thing as the set that has nothing in it. So you have wiggle brackets, nothing in it, like an empty bag, empty collection. That is also a subset. Again, subset is anything you take out of the larger set. Not necessarily anything really. You can take nothing, or you can take everything, or you can take anything in between and reassemble this set, and that would be a subset of that larger set. So that includes the whole set itself, that includes nothing like this, and includes anything in between. So in here, in the story about flipping a fair coin twice, I have actually 16 of them. Here they are. So I have the first event is nothing at all. The second one is one thing in it, HH. The third one is I have again one thing, HT. The fourth one is, I have one thing again, TH, and the fifth one is one thing again, TT. These are called singletons. Singleton is a set with one element, one thing in it, one element. So I took one thing in the sample space. The sample space has these HHHT, and I made a set out of that. So I have a separate bag now in which I have one thing in it. These guys are singletons. You could also have 2 things. So you can have HHHT, that's a subset. That you could call it, I could call it heads on the first toss. That could be heads on the first toss, heads on the second toss, heads on the first toss, tails on the second toss. So that's an event. Event doesn't have to have a name. It can just be any subset without a particular name. And again, I have HHTH, I could have that. I could have HHTT, I could have HTTH. I guess I would call that one heads, one tail. So it could be heads on the first toss, tail on the second toss, or tail on the first toss, heads on the second toss. And I have HTTT, and I have THTT. So here I have 6 different sets with 2 out of 4 of these guys. Okay. Then I have, so you can see a little better here. So it's an empty set, singletons, then 2 out of 4, and then I could have 3 out of 4. 3 out of 4. Now in the first one I was throwing out TT, so I took everything but TT out of the sample space. The second event, I took everything from the sample space except TH. The third event here, for the 3 out of 4, is that I have everything but the HT, and the last one is I have everything but HH. So I tossed the first one out. And finally, I have the whole sample space itself. So count how many events I have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different events. Okay. In the case of a blood type, like it could be, let me think about it. I think you have 256 different events here, and I'm definitely not going to try to write them down, but here is one of them, is this guy here. I have the A minus, B minus, AB minus, O minus. Obvious code for that would be a call, I'd say negative blood type, right? Either A, B, AB, or O, but negative. Okay, that would be an event. And again, there are 256 of them, so I'm not going to attempt to write them down. You can maybe entertain yourself. What's an event if I'm tossing the marker into this board? I guess anything that is made out of some points from that board. So for example, I would have this circle to be an event. If somehow the point that I'm hitting on the board is in the circle, within the circle inside. It could be also the circle at the edge. That is also an event. But if I'm talking about the whole thing inside and the edge, then I'm talking about all of the points that are inside the circle. There are infinitely many of them, so that's an event also. Okay? So again, the problem with this sample space, not a problem, but the difference of this sample space and those other sample spaces is that this one has infinitely many things in it. So you have to find some better way to write down the subset. The description, I guess, would be for a circle. The description would be given. You need to have the center and the radius, and then you would describe what that set is. But in either case, I would have, this is one event. You can have anything else you want. You can have, like, 2 points would be an event. Any 2 points you take also. Okay, so now the question is, finally, once we have the notion of experience, notion of outcome, notion of sample space, and the notion of event, what is a probability? That's a good question. The probability is, we are going to define a probability as an assignment. Now, this is known in pre-calculus and algebra as a function. So probability is some sort of an assignment, a function. But when you have an assignment, you're assigning something to something. So we are assigning numbers between 0 and 1 to an event. That kind of assignment might be a probability. Now, the idea of probability is to be a chance. So the number must be between 0 and 1. Could be 0.7, or if you want to talk about percentages, it would be 70%. 0.7 is 70%. So it has to be a number between 0 and 1. And it has to be with some properties. So we need to have some properties. We'll talk about that the next time we meet. But the idea is that probability is an assignment. So again, assignment of a number between 0 and 1 to an event. So you're assigning something to an event. That's one thing to remember. And what are you assigning is a number between 0 and 1. And you have to be able to assign that to every single event. We'll have some property. We'll talk about it next time. Those properties are going to be defining properties for what a probability is. So for example, if the assignment is to this guy that is an empty set, this is like saying nothing at all, the assignment must be 0 because something will happen. If I flip the fair coin twice, there will be some outcome. So the chance that this would happen, nothing at all, is 0. So assignment here would be 0. Every one of these 4 guys, excuse me, would have to have assignment of 1 out of 4. So this one would have 1 out of 4. This one would have, I think you probably agree with that, right? 1 out of 4. And the third one will have 1 out of 4, and the fourth one will have 1 out of 4. So I'm not going to write all of that. The idea is that there is a chance that you're going to get tails. The chance for that is 1 out of 4. Why? Because they're equally likely. So it's equally likely I'm going to get a tail head or head tail, or tail tails, or heads heads, and there are 4 of them, so it must be a chance of 1 out of 4. So that's my idea of a chance here. But I'm assigning a number between 0 and 1. You can see that, because 1/4 is 0.25. If you like decimals, that would be a number between 0 and 1. So that seems to be okay. Now, in these guys, they have 2 elements. These events should have, every one of them, assignment of 2 out of 4, which you can say 1 out of 2. Again, the chance that you're going to have 2 of these 4 must be 2 out of 4, because they're all equally likely. There are 4 of them, so if you are assigning probability on the heads on the first toss, that must be 2 out of 4, or 1 out of 2. It makes perfect sense, because the chance I'm going to get heads on the first toss is 1 out of 2. It doesn't matter what it's going to be on the second toss. So it looks like a 50%. And you can argue, as if you like, you spend some time thinking about it, but every one of these guys have a chance of 1 out of 2. Okay, every one of these guys in the 4th row has a chance of, I guess, 3 out of 4, because there are 3 out of 4 from the sample space. And the chance of the sample space, which means something will happen. Now everything that might happen is in the sample space. So since we know that something will happen, and everything in the sample space, then sample space must have an assignment of 100%. Something will happen. So you have here events that some of them are assigned 0 or 1, some of them are assigned, 4 of them are assigned 1 out of 4, 6 of them are assigned 1 out of 2, and 4 of them are assigned 3 out of 4 as a probability, as a chance. Okay? We will verify this down the road, that this is indeed a probability, because it has to have certain properties. You can't just randomly assign. I can say, oh, let's put this guy to be 1 out of 2, this one to be 73%, this one 22%, this one 0.3 or 30%, and so on. You can't. That would not be probability. That would be an assignment, again, of a number between 0 and 1. You would assign that to every event, but it would fail certain properties the probability is going to have. It would not be a probability, okay? So that's an important thing to remember. Blood type. Now, assignment to a blood type would be a little bit of a problem, okay? Now, you can say, what is the chance that I'm going to have a negative blood type? You can say 1 out of 2, because I'm either going to be positive or a negative blood type, right? I am personally positive blood type. My wife is positive blood type. Most of you are positive blood type. So which means then you realize, wow, it's more likely to be positive blood type than a negative blood type. Why is that? Well, they're not equally likely. That's the problem. These outcomes, A plus, A minus, are not equally likely. The kick is that the positive blood types are a lot more often than negative blood types. So the blood type distribution is statistical. Blood type distribution by country. So I'm going to think about the United States here. Where is United States? So even if you go from country to country, it's different distribution. But in United States, we have 37% blood type to be A plus. No, O plus, excuse me. And then A plus, B plus, AB plus. The first 4 are for the plus blood type. 37.4%, 35.7%, 8.5%, 3.4%. Those are the O plus, A plus, which is my blood type, AB plus, and O plus. Oh, excuse me. This is B plus, this is AB plus. Too bad I can't see all of what is on the top, but that's the idea, I guess. So, and if you go to Venezuela, like in Latin America, it's even more. But in the United States, it's 37.4% O plus, 35.7% A plus. So just these two blood types are already 73%. And then you have another 12% is in the B plus and AB plus. And there's a very small chance that somebody will be negative blood type. It's not very small, but it's a small chance. So we have a total of 12, 13, 14, 15% chance that you're going to be negative. So it's not 1 out of 2. That's one thing to remember. So in case of these guys here, they're not equally likely. These guys are not equally likely. Okay. So I'm having a little bit of a problem. What am I be assigning here? Well, you will be assigning the statistical distribution. So you're going to have to do some research to find out when you are dealing with the set of negative blood type. I was just sort of calculating like 15%, so you would assign a 0.15 to this guy. Any other set that would be an event. So an event is anything out of this sample space. There are 8 things here. You can have 256 different events. For every one of those events, you would have to use a statistical distribution to find out what is in, what are you interested in, and then add it up. So if I'd be talking about what I want, like A blood type, so I have A plus and A minus. That would be a blood type that we will call this event A blood type. So you need to find out how many are, what percentage of people is A plus, what percentage of people is A minus in the United States, add it up, and there will be assignment of a probability that somebody at random would be tested as A blood type, right? So It's a different way to determine that. But one way or the other, once you have this assignment of a number between 0 and 1 that will meet certain properties, those properties we'll talk about it the next time, but it would meet those properties, then you would have a probability. So probability is assignment of a number between 0 and 1 to every single event. It also needs to meet certain properties. So we're going to talk about it the next time. Okay? If the events are equally likely and there's a finite number of them, then all you have to do to assign the probability, all you have to do is to count. So when you're talking about what is the chance that you're going to have at least one head on a double flip of a fair coin, when you know that the sample space has HHHT, THTT 4 outcomes, and the set, the event you are interested in, has 3, then the probability is 3 out of 4. Meaning we are using this formula. Probability of an event is the number of outcomes in the event, frequency of the event, how many things you have in that event, 3. What is the total number of outcomes? How many things are in the sample space? You just have to count 4. The probability is 3 out of 4. But this must happen. You must have the events that are equally likely, and the number of them must be finite, because you can't really divide with the infinite number, right? So that makes sense. Okay? So when you look at my example of hitting a board with a marker, and if this is my event, I'm having a little bit of a problem here. Even if every single point to be hit is equally likely. If I'm not aiming, then that's true. How would I determine what's the probability of this guy here? Okay? Now, here is the idea, which is actually idea that we use in probability all over the place. You would actually calculate the relative area. So you're going to have to find the area of this circle relative to the whole board. So this circle might be at 10% of the whole area. Then the chance of hitting this circle would be 10%, 0.1. Okay? Or something else, depending what this is. Right? You would have a little bit of a problem here. The problem would be, what is the chance you're going to hit this line segment? 0. Because it has no area. The area of this line segment is 0. So when you have infinite sample space, there are infinitely many points here, and I'm using the idea of an area to be the idea relative area, to be what the probability is. So relative area meaning the area of the object relative to the area of the whole board. In case of a circle, I could say this is 10% of the board, so the chance of hitting the circle is 10%. In case of a line segment, I have 0 for the area. So the relative area of this line segment to the board is 0. The chance of hitting this line segment is 0. Now this gives you another idea about probability. The probability is an important idea about probability, is that something could be negligibly small in terms of a probability, but not empty. So that event, that line segment, is not empty. I have some points on that line segment. Yet the probability I'm going to hit those points is 0. This is what we call negligible probability. It could happen, but the probability is 0. So it's possible, but not probable. All right? People usually have this problem with this idea that something is possible, but not probable. Meaning, it's not empty. It contains some points, but probability of that set, that event, the chance of me hitting that line segment is 0. Okay? So we are going to call those kind of events negligible. That's not going to happen if you have equally likely and finite number of outcomes. Like in these examples, we have the rest of them, these three examples we are using. Okay, this would be simply calculated by using this formula. So if the sample space has equally likely outcomes and the number of outcomes is finite, the probability of any event is going to be the ratio of the frequency of that event, how many things are in the event, relative to how many things are in the sample space, the frequency of the whole sample space, the size of a sample space. Again, another thing also people usually don't understand, or students don't understand, is that the sample space is something to be related to sample. No, it isn't. Sample space is not related to sample. We're not talking about sample. We have a name for the sample space, the set of all outcomes. We call that sample space. But that doesn't mean it's a set of samples or that is a part of a sample or anything like that. We're not talking here about statistics. We're talking about probability here. Okay? In general case, when you're dealing with something like this over there, and we want to find out the something that would be a good description of what the probability is, we would use something called a distribution function. And the distribution function would determine what the probability is. That is a notion that is separated from the topics we're going to be talking about it, so I'll just put it in. So it's always possible to assign numbers to all of the events that came out of any sample space. So on any subcollection from a sample space, you would need to have an assignment of a number between 0 and 1. Probability that would meet certain criteria, certain properties. But that is usually given by something we call a distribution function. So it's not that we're going to be thinking every time, oh, what would that be, like in this case, an area or the count and stuff like that. No, we actually would have a very precise notion of distribution function, but we're not going to be talking about it in any details in our class. So let's have the one more example. I have here an example of sample space that is made out of 36 things here, and it's a sample space that is a coded outcomes of a roll of a pair of dice, gambling dice. So you could have something like a 3-4, which would be white with the black dots or red with the black dots. So you would know exactly what is the first die for you. The white the first die, the red the second die, or vice versa, whatever you want. Okay? And that is a different outcome than the outcome that would be 4-3, which will be 4 on the first die and 3 on the second die. Okay, so I have all possible outcomes here. So again, these are codes. I don't mean here 35. I mean 3 on the first die, 5 on the second die. So these are codes. Okay? Now, you can ask yourself any probability of any event here. So this is actually the whole sample space. Then put the wiggle brackets. You can easily put the wiggle brackets here at the beginning, at the end, separate them all with a comma, and determine any probability you might be interested in. I guess we all have an idea what the probability would be. Now, how would you determine that? Well, you need to think about that. And I think the idea would be that I'm going to use that formula I just mentioned. So the formula says the number of things that are in the event relative or divided with the number of things that are in the sample space. So I already have 36 things that are in the sample space. So if I'm asking you about a probability in particular here, let's say we talk about the probability of, this is my symbol for probability, it's symbol we're going to use, probability of what? Let's see, probability an event would be the sum is 9. What is the chance that if you roll 2 dice that you will have the sum on both dice to be 9? Okay, so if you want to write that in terms of an event, I would have to use the notation. So again, the brackets means probability of. So the P and with brackets means probability of. Probability of the sum is 9. As an event, the sum is 9. The sum is 9 is an event where you have 4 different outcomes. So that could be 3, 6, 6, 3, 4, 5, and 5, 4. There's nothing else. So if you roll fair die twice, or if you're rolling 2 fair dice once to get 9 as a sum on both rolls or both dice is 3, 6, then you have 9, 6, 3, you have 9, 4, 5, you have 9, and 5, 4, you have 9. There's nothing else you can have. These are actually the guys on this diagonal, this minor diagonal. 3, 6, 4, 5, 5, 4, 6, 3. These guys. There are 4 of them. Relative to the whole sample space, which have 36. That is 4 out of 36. In other words, I have probability here 1 out of 9. 4 out of 36 is 1 out of 9. Or if you like decimal numbers, that would be 0.11111, and on you go. 1 with a bar, right? About 11% if you go for the nearest percentage. The chance to get a sum 9. And again, I found that this way. I was using this formula. This requires that I have equally likely outcomes. I do. I think to get 4, 2 on the first die, 4 on the second die, or to get 5, 6, 5 on the first die and 6 on the second die is equally likely. We could argue that. We could talk about that a little longer. Maybe it requires some argument, but I think the common sense will tell you that this is equally likely. Every single outcome in those 36 outcomes of the sample space is equally likely as any other outcome. That's one thing. Another thing is I have finite number of the outcomes. Yes, I do. I have 36 of them. So I am meeting this criteria for the formula for the probability. The probability with equally likely outcomes and the number of outcomes to be finite is calculated by this following formula. And so now I was doing that. I have the 4 things in my event. I was interested in an event where the sum on both dice is 9. And I found out that I have 4 things in it. 6, 4, 3, 6, 6, 3, 4, 5, 5, 4, 4 out of, so that would be numerator, out of 36, which is denominator, total number of outcomes, the number of things in the sample space. We call it sometimes frequency of the sample space, or the size of a sample space, and the frequency of the event. And I was using this formula. By this formula, it's 1 out of 9, or about 11%. That's the idea, to use this formula. Blood types, probability of blood types, obviously I cannot calculate by using this formula because the outcomes are not equally likely. The outcome of having a A+ blood type is much more likely than having a B+ blood type, or some other outcomes you choose. None of the 8 outcomes is equally likely as any other outcome. So you cannot use this formula because you don't have equally likely outcomes. In this case on the board here, Again, you cannot use this formula because the total number of outcomes in the sample space, which should be in the denominator, is infinite. And of course, in most of the cases on any object on this board is going to be infinitely many points in there, in any shape, right? And then you wouldn't have anything finite on the top either. So you cannot divide with the infinite, or you cannot divide infinite with an infinite, so you would not have the probability by this formula. And again, in this case, every outcome is equally likely as any other outcome. Any point is equally likely to be hit as any other point if I don't aim. So I do have equally likely outcomes, but I don't have finite number of them, so I cannot use this formula. So the formula would be unusable because of the number of outcomes is infinite, and or if the number of if the outcomes are not equally likely, so in the case of blood type, again, I cannot use this formula. This formula is useful, but only when you meet both of those things, equally likely outcomes and the number of outcomes is finite. Okay, the next time we meet, we're gonna discuss this story a little bit further. We're gonna be talking about the properties of probability. I'm just gonna give you a brief introduction into that. In the 1930, so that was 90 years ago, great Russian mathematician Kolmogorov. Now I'm not Russian, so I don't know how to pronounce it properly, but I think they're pronouncing Kolmogorov. I don't know exactly, but he was one of the greatest mathematicians of the 20th century. So he wrote a book that he called Foundations of Probability, in which he basically laid the foundation, for the modern treatment of how we consider what a probability is. And in that text, in that book, he specifically listed the property probability must have to be called probability. First of all, he went with the idea that the probability must be an assignment to an event. So whenever you have an experiment, you will have, when you have an experiment, you will have an outcome. Once you have an outcome, you will have the set of all of outcomes, or we call a sample space. And once you have a sample space, you can get an event. Anything that is a subset, sub-collection from a sample space is an event. Now, according to Kolmogorov, you need to have, if you want to have a probability, you need to have an assignment of a number between 0 and 1 to every single event. How are you going to do that? It's a different story. You might have this formula we just mentioned. You might have something else like area, relative area, in the case of this whiteboard, or it could be something else like a distribution function that I mentioned. And now you need to have this assignment, this type of assignment you're doing. You must have the assignment to fit certain properties. Those are his properties. Now I'm not going to introduce them literally. I'm going to introduce them with a little modification, because the properties he listed of importance were only 3, but they involve a little more serious mathematics that we're going to have. So I'm going to list a little less restriction than what he had, and I'm going to list these 6 properties that we're going to use. Okay, we are going to also use some notation that I already mentioned. Notation like this means probability of A, where A is an uppercase letter that I'm using. Going to be a label for probability of. So it's a P, probability of. The container means of, and in the container will be an event, like the positive blood types. That will be 4 of the outcomes, right? Or anything like that. So this will be a notion of event. So I'm going to list, and we're going to discuss the next time we meet, 6 of these properties that must happen for the assignment of a number between 0 and 1 to every event to be a probability, right? And so we have a formal notion of the probability that we're going to discuss in the next lecture. So I am going to finish the lecture, and I'll see you the next time.